All right, so still missing two, but I'm sure they'll show up at some point. All right, guys, so today we're going to try something a little bit different. It's my first time trying this. I've actually got a document camera set up, so I can actually write out notes on a notepad. So we'll play with that a little bit. And then I will also, I've got some screen sharing stuff that we can do as well for some examples. So let's give this a shot. Make sure this is the right spot. There we go. All right, so today we are going to talk about error, and kind of in a broad sense, and then kind of get towards kind of the specifics of what error in elevation measurements and in topography data really kind of means. And this kind of goes towards what you guys are doing in lab 3, with part of the last part of the lab is to do some error analysis in a very basic sense. So in kind of a statistical sense, what is error? Does anybody have any thoughts on what error is?
The variance of the values for the data for the versus the actual real life values.
Yeah. So in a kind of in a very practical sense, if we think about it like an equation, okay, we can think about the value E is the error in a measurement, okay, is equal to the measured value, okay, minus the, and we're going to use this kind of, okay, the true value. Okay, so whatever value we measured minus the true value of that point. Now, the question is, how do we know what that true value is? Can we ever know what that true value is? And so the answer is no. Okay. This is why, again, we have this in quotes here, is that there's no way to really know what the true value of any measurement is, okay? And that's kind of a whole philosophical discussion in kind of the philosophy of science. But the reality is that this true value really is okay. Usually we just think about the true value as is a value that's measured with what we call higher precision. And we'll talk about accuracy and precision here in just a second. But generally speaking, in the sense of our topography data, when we're talking about the measured value versus the true value, generally we're thinking about, okay, the measured value is going to be something like, you know, a DEM point. You know, from a DEM we can download from the USGS, or a LiDAR data set, you know, a LiDAR point on the ground. Those are our measured values generally. And then in order to kind of gauge the kind of true value, we usually go out and measure that point with an instrument of higher precision, a more accurate instrument. So in this case, we could go out with something like a total station. We could go out with a terrestrial laser scanner, which is higher precision. Okay, we can do a lot kind of in this sense to get this kind of, you know, again, in quotes, the true value. Okay, and so generally when we're talking about the true value here, we're just talking about some value that we've measured with better accuracy and better precision. Okay, so the idea of error, okay, there's two concepts in kind of error analysis. Okay, so error, okay, is when we talk about error, we talk about an individual measurement. Okay, so any individual measurement that we make, okay, has error associated with it. Okay. We can aggregate that error in a couple of statistics that we'll talk about today. But then there's another concept which is a little bit bigger, which is okay, the idea of uncertainty. Okay, and so this is okay, both the known and unknown errors in a data set. Okay, and that accounts for all of the error that we see. So this second concept here, this unknown error, is something that we'll talk about. But again, because we can never know the true value of any measured value that we, anything that we're measuring out in the environment, okay, because we can't ever know the true value, there's always going to be an unknown source of error. Okay, and again, we could go, there's whole books on this. I have that book here. I don't think I do. It's up at school. There are whole books on error and uncertainty analysis in statistics and in other branches of science. So we're not going to get into this completely, but this just get these two terms we'll use kind of, I use them kind of interchangeably, but specifically error relates to an individual measurement versus uncertainty is kind of both those unknown or those known errors that we can measure and the unknown errors that we can't measure. So some kind of some universal kind of facts about error. Shrink myself down here just a little bit. Okay, is that okay? Okay, no measurement is exact. Okay, is our first kind of statement or universal kind of a fact about error. Okay, and this all comes down to the devices we use to measure. Okay, and so in a very basic sense, if I have a tape measure here, okay, there's inaccuracies in this tape measure. Okay, it was produced on an assembly line. Okay, it's reasonably accurate, but it's not exact. Okay, and one of the things to think about with this is that on a tape measure like this, okay, or a ruler, okay, whatever you want, okay, however many rulers and tape measures you want, I've got a whole bucket of them. Okay, part of this is that we only go down to a certain number of divisions on the scale of our rulers. Okay, and so this goes down to, like, on this ruler, or my rulers, or the tape measure here goes down to about a 1/16 of an inch. Okay, is the smallest kind of reasonable measurement we can make. On this silver ruler is a machinist scale, and this goes down to about 1/2 millimeter. Okay, so even better than about a 1/16 of an inch. Okay, so with reasonable accuracy, we can get down to a 1/16 of a millimeter, or a 1/2 millimeter here. Okay, and then if we want to get even better, okay, we can bust out our calipers. Okay, and so these measure, can measure the width or height or depth of anything. okay, up to a certain, I think this is 6 inches, but this can go down to 0.02 millimeters. Okay, is the accuracy of this. So if I measured something like the width of my pen here, I can tell you with a certain amount of accuracy that that is 10.06 millimeters wide. Okay. Versus if I tried to use a ruler on this, okay, my estimate, I'd have to kind of estimate because it's about, it kind of covers about a centimeter or 10 millimeters, but I really can't get more exact than that. Okay, so it's approximately 10 millimeters. Okay, versus with a higher accuracy measurement device, okay, I can tell you that it's 10 point, well, yeah, 10.06 or 10.08, depending on where I am on the marker. And so, the exactness of a measurement depends on the instrument that we're using to measure. Okay. Now, is this the exact width of this marker? Again, no. Okay, because this only goes down to a certain number of divisions. Okay, 0.02 millimeters, but we could get even better with better tools. Okay, but the fact is that I can never actually know the exact measurement of, okay, this pen. And that goes outside when we're measuring terrain. Okay, same thing applies. Okay, we can measure it with radar, it'll give us one number. We can measure it with LiDAR, it'll give us another number. We can measure it with GPS, we'll get another number. We'll measure it with a total station, we'll get another number. Okay, chances are they'll be within a certain kind of range of each other, but there's no such thing as an exact measurement. Okay, we can get more accurate and more precise, but there's no such thing as exact. Okay, the true width or the true height or the true measurement of anything, okay, can never be known. And that's kind of the philosophy of the day when we're talking about error in measurement. Okay. So 2 on here, okay, kind of associated with that is that every measurement contains errors. Okay. So again, depending on our measurement device, okay, those errors can be relatively large or relatively small. Okay, but the errors are there. Okay. Just so you can think about this in terms of kind of the errors associated with that. My calipers actually came with a calibration certificate. Okay, and the errors in this are very, very small. Okay, so in terms of let's see, in terms of millimeter lengths, okay, the permissible error on this, okay, is about 2/100th of a millimeter. Okay, and for all of the measurements that they made, it's within that error range. Okay, but again, we can't ever know, so that's just the level of error that's associated with that measurement device. All right, and then 3, okay, and this goes kind of back to number 1. Okay, the true value of a measurement can never be known. Okay. And then this kind of leads into number 4. Okay. Okay, the exact error is always unknown. Okay, because we can never know the true value. Okay, we can never account for all of the error that we see in a measurement. Okay. So, some of this can be a little disconcerting because we can never know the true value and we can never know the true error. So why are we doing any of this? Okay. And so the trick is that we have different modes of measurement. Okay, again, a tape measure versus a ruler versus a caliper. Okay, different modes of measurement can get us better or tighter tolerances or looser tolerances on our measurements. And so the idea is that we can always try to get better measurements. Okay? And that's something that we should always try to do whenever we're, in any scientific endeavor. Okay? Whether we're measuring terrain or whether we're measuring, chemical reactions or whatever you're measuring in science, okay, that you always need to try to measure it in a better way, and that will help us quantify the error. Okay? And so the kind of key thing here is that knowing the error, okay, or estimating the error is generally the way we think about it, okay, is important. Okay, and the classic kind of example of this, okay, from countless textbooks and we'll call it pseudo history. I'm not sure how accurate this is. Okay, but it's one of those kind of examples that comes up over and over again in statistics books and throughout history. Okay, is the idea of kind of Archimedes, kind of classic Greek philosopher and mathematician. Okay. Trying to determine whether or not the crown of a king is made of gold or a metal alloy that looks like gold. Okay. And so this is just kind of a classic statistical example. Okay, so this is the Archimedes crown example. Okay, and so the trick with this, okay, is that we know, okay, or we can assume that okay, we can assume that we know that the density of gold is 15.5 grams per cubic centimeter. Okay, gold is relatively dense metal. Okay, it's heavy if you hold it. Okay, and that the density of a metal alloy, okay, that kind of looks like gold would have a lower density. Okay. Right. So we're going to assume that lower density is 13.8. Okay. And so if we were going to, the story goes that two experts were summoned. The king summoned two experts to his court in order to determine whether his crown was made of gold or not. Okay. And so expert one, okay, runs in and says, okay, we can do a quick measurement here. Okay, so expert one comes in and gives a quick measurement and says, I can approximate the density of the metal that's used in this crown to be 15 grams per cubic centimeter. Okay, but the error on my measurement is somewhere around plus or minus 1.5 grams per cubic centimeter. Okay, so a reasonable measurement, okay, but with a fairly large error associated with it because it's a quick measurement. Okay, and then we get expert two comes in, is a little bit more methodical. Okay. And does a more detailed measurement. Okay. And so the second expert says, okay, my best estimate based on my experiments shows that the density of the metal in the crown is 13.9 grams per cubic centimeter. Okay, and I'm fairly confident in this that it's plus or minus 0.2 grams per cubic centimeter. Okay, so the idea is that, you know, two experts come in, one gives a quick measurement, one makes a more detailed measurement. Okay, and the results, if you just relied on one or the other, okay, expert two is obviously a little bit more accurate, so that's definitely something we can put more weight in. But if we look at this in terms of number line, one more color out of my bag here. Okay, so if we think about this in terms of the error associated with a measurement. Okay, if we have, say, okay, if we have a number line here, 13 to 16. Okay, and then if we plotted the, or let's say let's plot the values that we know. Okay, so gold is 15.5. Okay, right there, and then our alloy is 13.8. Okay, so about there. Okay, and so if we plot our measurements on here, okay, with error bars, okay, we get our expert one, okay, comes in at 15 grams, okay, but plus or minus 1.5 grams. Okay, so if we go minus 1.5, okay, that gets us down to 13.5, and plus 1.5, okay, takes us up off the page here to 16.5. Okay, so a fairly large error bar on that measurement one, okay, or expert one. Okay, and then if we look at expert two's measurement, okay, 13.9, okay, so right here, okay, plus or minus 0.2 would get us up to 14.1. Okay, and then down to 13.7. Okay, so if, you know, if we look at just expert one, okay, in this case, okay, so the green line here, okay, if you just said, okay, I'm going to make a quick measurement, I give you 15 grams per cubic centimeter, okay, well, that's close to gold, okay, up here. Okay, so you might be inclined to suspect that, well, it's 15 grams, okay, so it's probably gold, okay, weighs a lot, so it's closer to gold than it is to the alloy, so maybe we'd assume it was gold. But if we take into account the error bar on that measurement, okay, that error bar actually encompasses all the way down to the density of our alloy and the density of our gold, okay, and so what we can, the only thing that we can say about this measurement is that we can't be confident that it's either one. Okay, it could, there's an equal chance that it's alloy or an equal chance that it's gold. Okay, because it's within those error bars. Okay, versus if we look at expert two, in this case, okay, 13.9, okay, was the measurement. Okay, that's close to alloy and quite a ways away from gold. So we can be maybe more confident that it's alloy versus gold. But within our error bars, okay, the alloy measurement falls within our error bars. Okay, but gold is quite a bit of ways. Okay, and so we can say with confidence in this case, in the measurements of expert two, that, you know, the density is 13.9, and that's close to the alloy, and that alloy measurement is within our error bars, so that we can say that with a certain amount of confidence, okay, that the crown is made of an alloy and not pure gold. Okay, and so this, if we think about this in terms of terrain data, okay, the common place where something like this comes up is when we're talking about change. between like time 1 and time 2 in a landscape. Okay, and so if I've got two, I'm just going to draw 2 terrain profiles here. Okay, so if I've got terrain profile 1 here, okay, and terrain profile 2, let's say there was a rainstorm and we had some amount of change in our landscape. Okay, so the difference between these 2 lines would be a vertical change in the landscape. Okay. What we want to make sure when we're measuring change in a landscape like this is that the error in our measurements, or that the change is greater than the error in our measurements. Okay. So if we had a, let's say we measured our first terrain points, okay, on the blue line there, okay, with a fairly wide error bar, okay. So we just went out and we estimated it with a very, let's say we just estimated it with the GPS on our phone. Okay, so that's plus or minus 3 meters. Okay, and we go back out and we say, okay, well, we estimated the height before with a fairly coarse measurement technique. Okay, and we can go out with, again, measure after the rainstorm to measure the change. Okay, and let's say we're going to measure our terrain points on the green line here with a more accurate GPS. Okay, so we have a much smaller error bar on that measurement. Okay. The problem here is that if we difference these 2 elevations, okay, we'll get a change, okay, something like, let's call it minus 2.1, okay, would be the change. But because of the error bars on our first measurement and the error bars on our second measurement, okay, we have to include a plus or minus value on this. Okay, and so if we measured the first one with a really coarse measurement, it's going to be plus or minus about 3-ish meters. Okay, and so in this case, the problem is that because our first measurement is made with a fairly coarse measurement tool, okay, we'd have to incorporate that error into our measurement, and we'd say, well, the difference between the first surface and the second surface is minus 2.1 meters, okay, but it's plus or minus 3 meters based on the error in our measurement. And so in this case, okay, just like in experts 1's case, okay, we can't actually, okay, with statistical confidence, say that there is any change in this landscape, okay, because the change is inside of our kind of error measurements. Okay, if the change was bigger than our error, we could say with a certain amount of confidence that it was real change. But if it's less than our error in this case, okay, we can't actually say that it's statistically significant change. All right, questions on that? All right. So let's talk about some sources of error. Okay. So the first type of error that we see in measurements, okay, is what we call natural error. Okay, so these come from what we call natural phenomena. Okay, so things like wind affecting your measurement, temperature affecting your measurement, okay, humidity might be affecting your measurement. Okay, so things that are kind of natural in the environment that might affect your measurement. Okay, we refer to those as natural errors. Okay, the second is what we call instrument error. Okay, so this is Okay, error that's just inherent in the instrument. Okay, and so in most instrument cases, okay, and if you're using kind of more precision instruments, okay, you're going to they should be calibrated to a certain level of kind of confidence. Okay, but the fact is that again, every instrument is going to have error associated with it. Okay, so if we go back to our tape measure example, okay, this has a certain amount of error associated with it because it's, you know, it's printed using a certain technique on a kind of curved metal surface. Okay, and so there's a certain amount of just error inherent in this. Okay, now it's, again, it's fairly accurate down to a certain level of measurement, but you know, there's still going to be some error in here. Okay, and then, you know, I don't know if anybody's ever noticed, but you know, the little tab on the end of your tape measure, okay, actually moves a little bit. Okay, and that's part of the design, but that little bit of movement in the little tab when you hook onto something, okay, or push it up against something, okay, that's a source of error, okay, that's built into the instrument. Okay, there's a little bit of error in there. Okay, again, back to the calipers. Okay, these are calibrated to a certain level of precision, but you know, this is kind of the dial on these calipers is driven by some gear teeth. Okay, and here, let's see if I can show you guys this. Maybe. Okay, there. Okay, so you can see these little gear teeth inside here. Okay, and so that dictates the precision that this can measure. Okay, so if there's any inaccuracies in the way that those gear teeth were manufactured, okay, there's going to be inaccuracies in the caliper itself. Okay, and same thing goes for our terrain measurement devices. Okay, so you know, a total station, okay, can only be so accurate. Okay, it's measuring the time of flight of a laser pulse, and you know, it can only measure that to such a degree that, you know, we can measure down to kind of maybe tenths of millimeters, but we can't do much better. Okay, and so there's a certain amount of instrument error built into every instrument. Okay, next is they're called processing or calculation errors. Okay, and so this is just okay, errors introduced by doing calculations on your data. Okay, and so this can be something like, you know, something as simple as doing a unit conversion. Okay, so from, you know, feet to meters, okay, from terrain data, Fahrenheit to Celsius. Okay, there's a certain amount of error associated with those calculations. Okay. Okay, another source of processing or calculation error, okay, which is a big one, okay, is rounding errors. Okay, and this is, you know, again, if you have a big long decimal and you truncate the number of decimal places, okay, or round up or round down on a number, okay, that's going to induce a certain amount of error because you're kind of leaving out part of the measurement, or you're physically changing the measurement. Okay, so you know, so if you go from 0.1226, okay, and you round up to 0.123, okay, this, you've just added an error there, okay, because the value that you actually measured is 2.6, you rounded it up to 2.3, okay, so that's 0.0004, okay, error, but, and it may not seem like a much, but you know, if you do this on every measurement across an entire data set, those rounding errors can add up. Okay? Not to say that you shouldn't do these things, okay? You should always convert, and you should potentially always round, okay? But these do introduce some error. Okay? And then the last type of error okay, or what we call blunders. Okay. Okay. Also known as humans are not perfect errors. Okay. Is that these can be things that you just screw up. Okay. So these can be probably the most common. And I've done this countless times, okay, is what we call transcription errors. And so these are things like if I'm reading off measurements, okay, off of my GPS or my total station, and somebody else is actually physically recording them in a field notebook, okay, I might say the distance was 76.532, okay, but then you write, so if I say 76.532, okay, but then you write something like 76.523, okay, which is, again, a fairly common thing that can happen, okay? So this is wrong and this is right, okay? But this is what gets recorded in your notebook, okay? That's a blunder of an error, okay? That's a transcription error. Now, could you fix that? Yeah, you might be able to discern that 3 and 2 are backwards, okay, because the rest of it's the same. Okay, so if something is way off, you might be able to correct for that, okay, but not always. Okay, another thing is okay, blunders can be related to your senses as well. Okay, so like how good is your vision? Okay, so like on my machinist scale here, okay, so if you zoom way in on that, okay, you can see that the bottom scale has 0.5 millimeter divisions of it. Okay, so if I've got this down on my page here, okay, and I'm trying to measure something. I've got a slab of marble from an art project, okay, but if I'm trying to measure this, okay, the width of this piece of marble, okay, part of the blunder could be that like I'm looking down at this and I see, my vision's not that great today. I've got something in my eye, so I'm going to say 75 millimeters, okay. But if I get out my reading glasses, okay, and I put on my reading glasses and I actually have some magnifiers on here, I can actually get down there and say, oh wait, it's not 75, it's actually 74.5. Okay. So blunders can be made based on kind of your vision, okay, or transcription errors, okay, or if you're looking very quickly at, say, a tape measure, okay, you could, mistake a 2 for a 3, or mistake, different things. Okay, so your senses can mislead you, basically. Okay. And so blunders, again, we call them blunders because they're literally just accidental errors that are introduced into the data sets. So those are the sources of error. Okay, so if we think about this in terms of types of error, okay, so kind of two different ideas. Sources of error are the natural errors, the instrument errors, the processing errors, and the blunders. Okay, and then so we can kind of classify those into types of errors. Okay, so again, the most common, okay, are what we call mistakes. Okay, so mistakes are things like blunders, or you pressed the wrong button on your instrument. Okay, that'd be considered a blunder. Okay, so mistakes are something that's potentially fixable in your data. Okay, so you can, if you can recognize it and with confidence say that you did something wrong, okay, you can potentially fix that. Oftentimes these will get we call thrown out of a data set. Okay, so if you're measuring along and you're out surveying topography, okay, and let's say you're holding up your total station rod and somebody, your colleague's taking the point and you sneeze, okay, and all of a sudden the instrument of the pole that you're holding is now forward 20 degrees. Okay, that's a mistake. Okay, and so could you fix that? Well, yeah, you could stand up and tell them to retake the point. Okay, but that point you took, okay, has lots of error in it. It was a mistake. And so generally what you would do is just delete that point out of your data set or throw it out of the data set. Okay. The second type of error that we see in data sets are what we call systematic errors. Okay, so these affect the entire data set. Okay. Okay, and you can, again, there are ways that you can recognize this, okay, and correct for it. Okay, but an example of this, okay, is that let's say your your tape measure was 2 centimeters too short. Okay, let's say there was a knot. And say, like, if you have a fiberglass tape that's relatively flexible, there was a knot in it that you didn't notice. Okay, and so every measurement you took, okay, for the entire data set is 2 centimeters too short than it should be. Okay. Now, if you can identify that and recognize it, and then say, okay, all the measurements aren't coming out quite right. Okay, let's say you go back, you can figure this out by going out and remeasuring something and saying, well, with a different tool, and saying, well, all of the measurements that I'm getting with the second tool are 2 centimeters longer than my first one. Okay, and so I can say that this is a systematic type error. Other systematic errors can be more complicated. Okay, and so things like in our GIS data, okay, let's say we're doing georeferencing. Okay, we can end up with systematic errors that are things like tilt in our geographic data. Okay, and so if we have a data set that's relatively flat, okay, like this, okay, and then we georeference it or do some conversion on it, and we end up with something that looks like this, okay, that tilt is what we consider a systematic error in the data set. Okay, that it affects the entire data set. Okay, and it's now tilted at 0.26 degrees, okay, from what it should be. Now, figuring out that something is tilted at 0.26 degrees is fairly difficult, okay, but it can be done. Okay, but this is just an example of a data set that's affected by an error across all of the data points, okay, not just individual data. Okay, and so the last type of error that we see, okay, is what we call random error. Okay, so random error in statistics, okay, is basically what's thought of as what's left. So the error that's still left in a data set after mistakes and systematic errors have been accounted for. Okay. Now, random error goes towards kind of a bigger concept, which is that, again, or that bigger concept that all measurements have error, okay? And if we can account for mistakes and account for systematic error, okay, there's still going to be a certain amount of error that's left, which is random. Okay, literally, you can think about this. Random error is things that are beyond your control, things that you don't know about, things that you can't control. Okay, there will always be a certain amount of random error in any data set. Okay. So random error is go there. Can't spell today. Okay. Okay. Random error is beyond your control. Okay. So again, it will exist no matter what. And no matter how accurate, how careful you're measuring and how precise you're measuring, there's always going to be a certain amount of random error, okay, in a data set. Okay. And you can usually see random error pretty well if you're using a precision measurement tool, okay, like a total station or like a caliper here in this case. And if you measure the same thing over and over and over again, okay, you're going to get slightly different answers. Okay, you're measuring the same thing with the same instrument, but you're going to get slightly different measurements, depending on kind of the position and how you're holding it, and a lot of that goes towards this idea of random error. All right, so next up is one of my favorite diagrams that I like to draw all the time in any GIS class. Okay. But this is to illustrate the ideas of okay, precision versus accuracy. Okay, so we've been talking about error. Okay, and so error is the amount that's, the amount that our measurement is off from the true value. Okay, and so when we talk about error, okay, generally precision and accuracy come into play because we can talk about precision as being how consistent our measurements are, and accuracy is then what the actual the kind of the smallness or the largeness of our error value is compared to our true value. Okay. So precision, okay, you can think about as consistency. Okay, consistency between measurements is the idea of precision. Okay, and then accuracy okay, is how near we are to that kind of quote unquote true value, the truth value. Okay, so if we have a very small error, okay, our measured value is very close to the true value, okay, we would say that we have a very high accuracy. If our error is quite large, okay, then we would say we have a low accuracy. Okay, our measured value is not that close to our true value. All right, so the way that we can kind of illustrate this is by playing a game of darts. Okay, and so we're going to play 4 games of darts. Okay, so I'm going to draw some rough dartboards here. Okay. And so the idea in our game of darts here is that the bullseye is our true value that we're aiming for in our measurements. Okay. And so if I go in and take some measurements, okay, or throw my darts, okay, and I end up getting a grouping of darts like this, okay, throw 5 darts, okay, I'm off of the bullseye, okay, but I've got a fairly tight grouping there. Okay, so this is the idea of precise but not accurate. Okay, so our grouping here is tight, therefore it's precise, it's repeatable, it's consistent. Okay, but we're pretty far away from our center point, okay, our true value there. Okay, so precise but not accurate. Okay. Okay, we could do another throw of the darts, okay, or another set of measurements. Okay, and we could get, let's say we get a little bit bigger spread on our grouping here. Okay. And so the idea with this is that if we averaged out all of those measurements, okay, kind of like I did up here in the green, okay, if we average out all of those measurements, we'd end up with something that's fairly close to the middle. Okay. And so in this case, this would be, because our average of our measurements, okay, is near the middle, okay, but our spread is fairly wide, okay, this would be okay, accurate but not precise. Okay, so a fairly wide spread, but the average of those gets us towards the middle there. Okay. The best of both worlds, okay, is that we have measurements that are right around our bullseye, okay, and so our average would be dead center. Okay, so in this case, this is okay, both precise and accurate. Okay, our measurements are very consistent, and they're very near our true value. Okay, and then just for completeness sake, the most kind of egregious example, okay, would be if we had a few too many drinks and missed the dartboard completely. Okay, and in this case, okay, we get our average point is way out here, okay, and so fairly far away. And in this case, this is okay, not precise or accurate. Okay. And so this is just something to be aware of, that when you're making measurements out in the world, okay, is that your kind of goal is to get to here. Okay, what you're aiming for is precise and accurate measurements. Okay, but you know, a lot of things go into how measurements are made. Okay, next up, your next best bet is to get accurate but not necessarily precise measurements. Okay, because then you're still, the average of your values is about right. Okay, and then these other two, so precise but not accurate, okay, can give you a false sense that you're doing the right thing because you have precise data sets. It's consistent, but it's not correct. Okay, and then what you always want to avoid is ending up with data that are not precise or accurate, because those are just useless data. Okay. All right. So in the best possible situation, okay, is that okay, so in situations where we can do repeat measurements, okay, so where we can measure the same distance multiple times, okay, so the idea would be, put your ruler down, measure it, take it away, put it back, measure it, take it away, put it back, measure it, take it away, okay. If we can get repeat measurements like that, that's kind of the best case scenario, because that helps us kind of evaluate, okay, precision and accuracy better. So there's a couple of different ways that we can do this. One is literally, making multiple measurements, okay, or if we're using a caliper, I can measure my finger and take it away and then measure it again and measure it again and measure it again. Okay. If we're out in the field doing surveying, okay, oftentimes the devices that we use kind of automatically do repeat measurements. Okay. A total station generally will take multiple measurements and give you the average, okay, automatically. Depending on how your surveying GPS is set up, I usually set mine up to take about 5 independent measurements, and it's actually taking more than that. Okay. And so this kind of is built into a lot of the kind of surveying and topographic data generation that we already do. Okay. But it's just this idea that when we can make repeat measurements, okay, this is kind of the best situation that we can hope for. Okay. And so when we have repeat measurements, okay, we can, okay, we can report what we call our best estimate for our value. Okay. Or you can also think about this as the most probable value. Okay. And so if we take multiple measurements, okay, the most kind of natural statistic to use to get this best estimate is literally the mean value of our measurements. Okay. So generally we think we symbolize the mean as x bar, okay? And so the equation for this is, okay, the sum of our measurements, okay, divided by the number of measurements that we've taken. Okay. So if we take 5 measurements, okay, we add all of our 5 measurements together, divide by 5, get the average value for those measurements. Okay. Now, again, in the case of our bullseyes, okay, what we're hoping for is that all of those measurements are about the same, okay, and the average comes out to about what our measurements were. Okay. Again, that's kind of what we're always aiming for. But in some cases, depending on your instrument, you may end up with this case, okay, hopefully. Okay. And then what we can do once we have this, okay, is we can look at the mean value, okay, the mean value for our measurement, okay, and then we can actually start to get the kind of the error. I'm going to use green here. Okay, we can talk about the error or the residuals, okay, for our individual measurements. Okay, and this goes back to that very first equation that we talked about. Okay, is that this is basically the symbol that we usually use for this is kind of a cursive kind of V, okay, for error, is okay. So we take our individual measurements, okay, and we can subtract the mean value, okay, from those measurements, and that gives us a kind of indicator of the error on that individual measurement. Okay, so this is like what we saw at the beginning, okay, which was E, the error is okay. Same idea, okay, so error is the measurement minus the true value, okay. So this, but instead of the true value here, because we have repeat measurements, we can actually use the mean as, again, our best estimate or most probable value in this case. Okay, so the mean then becomes a proxy, okay, or a substitute for the true value of that measurement. Okay, so another way to look at this, okay, is by, rather than saying repeating a measurement over and over and over again, okay, we can also kind of look at this in a bigger context for a data set, okay, so like a terrain data set that you guys are looking at in lab 3, okay, is by, rather than repeating measurements over the same spot multiple times, okay, we can actually look at multiple measurements across a data set as well, and look at kind of, we'll actually end up looking at mean error in this case. Okay. And so I'm going to get that off and get this up. Okay. And so I've got here, let me actually pull up the data set. Okay, so what you guys are going to be doing in lab 3 is basically looking at a series of different rasters that you've interpolated, okay, and basically extracting out the kind of the raster values for those interpolated rasters and comparing them to kind of the original LiDAR data points that were collected. Okay, and so this is not, let me, that's the output. Okay. So in this case, actually make this. So in this case, what we end up with, or what you guys are going to end up with in lab 3 is basically a table, okay, of Z values, and these are the original LiDAR elevations, okay, measured at several points around the map. Okay. And basically what we're doing here is basically comparing this original value to all of these different interpolated surfaces that we're playing with, okay, in QGIS. And so in this case, okay, you can see that this is the original value. And if we look at, this is an IDW, an inverse distance weighted surface, okay, and so that has a certain difference, okay, between them. Okay, here's a nearest neighbor one that's a little bit closer. Here's a tin one that's maybe even worse than the IDW. Okay, it's a little bit lower. Okay, here's another one of the other surfaces, okay, is actually spot on. Okay, so in that case, that would be we call a zero error point, and this point equals our measurement. Okay, and so you can see all of these. And so this just goes on and on. I think it's 150-ish points, okay, that you guys are going to be playing with. But the idea is that we can start to look at some of the error in graphical form too. And so you guys aren't going to be doing this specifically, but I just wanted to kind of give you a feel for what this looks like. Okay, and so one way, and I'm using Python here as a graphing software. You can do this in Excel just as easy. But so the idea is that if we pull in these data, okay, and in this case, what I'm going to actually do is create a plot that is looking at the, in this case, the x-axis is our interpolated elevations. Okay, this is just for one of the data sets. And the y-axis is the kind of what we call the validation data set, the true value. Okay, so every one of these points, we're basically looking at the measured value along the bottom axis here, the interpolated elevation, versus the true value along the vertical axis. Okay. And so if those were equal, okay, if the interpolated elevation equals the LiDAR elevation, these dots would fall directly on this dotted line here. Okay, that's we call the one-to-one line across this graph. So if our interpolated elevation was 1775 and our LiDAR elevation, okay, our truth value is 1775, we would plot that point right on that dotted line there. Okay, but what you can see is that we have points that are both above and below that dotted line. Okay, and so these are kind of positive errors above the dotted line and negative errors below the dotted line. And so another way to look at this is actually as what we call a residual plot. Okay, so this is actually looking at the individual points, okay, based on their error. Okay, so in this case, what we're looking at is the interpolated elevations along the x-axis again. Okay, but it's on the y-axis now, we're actually just looking at the error in those individual points. Okay, and so if the point is above the line, okay, that means that the interpolated elevation was, I think, higher than the LiDAR elevation. Okay, and so this is just kind of one way to think about errors in individual points. But basically, in this case, in kind of relation to the mean value, okay, what we would want ideally is that all of these would be near zero. Okay, so near the kind of, or that the average of all of these points would be zero. Okay, the error would be zero is the idea. Okay, but in this case, it's not. It's close, but it's not quite. Okay. I just wanted to kind of show you this in a plot sense to kind of tie it back in with Lab 3 real quick. All right. So in the last few minutes here, get my stuff organized here. Okay. Some of the other error statistics that you might see, okay, and that you guys are going to actually play with in lab, okay, is the idea of the what we call the mean error. Okay, so that's that little cursive V for error with a bar over it for the mean value. Okay, so the sum of all of the error values from our data set. Okay, so if we go back here, okay, so our measured versus our true, okay, or our predicted versus our measured versus predicted. Okay, so the sum of the error divided by, again, n, the number of observations that we have, and the number of measurements that we have. Okay, and so this mean error is our measure of accuracy. And then next up is what we call the standard deviation. Okay, so again, back to basic statistics here. Okay, so standard deviation we symbolize with the Greek small sigma here. Okay, and so standard deviation is the square root, okay, of, similar to up here, okay, we have the sum of all of our individual error values, okay, but we're going to square that. Okay, and then because statistics is funny, okay, we're actually going to do the denominator here, okay, is n minus 1. So the number of observations minus 1. Okay, and so standard deviation gives us some idea of the precision in our measurements. Okay. And then the last one for today, okay, and this is something if you've done any amount of GIS or remote sensing, okay, is what we call the root mean squared error statistic. Okay. And this doesn't have a symbol, but it's actually very similar to a standard deviation. Okay, the sum of our errors squared, and in this case, it's just over n. Okay, so very similar to standard deviation, but in this case, it's over n. Okay, and this is okay, call it kind of accuracy. Okay. It's not quite as good of a measure of accuracy as our mean error, okay, but root mean squared error is a kind of accuracy measure, okay, even though it looks very similar to our precision measure. All right. That was a lot of statistics for one day. Thank you for sticking with me. Okay. Hopefully Thursday will be a bit warmer and we'll be able to meet in the classroom. So stay warm, stay safe. Have a good afternoon.